All right, so just a couple of announcements real quick. Can you guys turn this down a little bit? So next time, for tomorrow, you guys should all be ready to give these short presentations on your design projects in recitation. We posted a sort of one-page guide talking about what it is that you should prepare for next time in class. These are short presentations. You shouldn't need to put too much time into getting them together. But please look at the webpage and just, if you're not sure what it is that you're supposed to be doing in class. So today, what we're going to do is we're going to wrap up our discussion of security. And what I want to do is I want to start off with sort of a fun little diversion, which is over the past couple of times that you guys were in class, we captured a log of all of the network traffic that was going on while people were in class on their laptops. And for the most part, it turned out that you guys were pretty boring. Nobody was actually doing anything very exciting, but there were a couple of interesting lessons. So in case you're curious as to what we actually did, this thing is almost cutting off the bottom of this, but so we ran this TCP dump command. So the sudo command just says run this command as though you are a super user, as though you are SU, and then TCP dump just says dump out all the traffic on the specified network interface. So in this case, it's dumping out all the traffic on EN1, which on this computer is the wireless network. So we're just dumping out all the packets that were sent out over EN1. And what you see here is the yellow part is the sort of header of the packet, showing you what saying this is an IP packet and specifying who the sender, the destination and recipient of this packet are. And then there's some body text, some sort of payload that's associated with this packet. So in this case, this first packet it's some binary data. We can't make any sense of it. But if you look at some of these other packets, for example, this is a packet that is a HTTP request packet. And what you see is that there, in fact, is English text. So the HTTP protocol uses English text to transmit information. And so this is specifying some information about this is the actual HTTP request going out. In this case, it was going out from this laptop. I just set this up as to illustrate what TCP dump does. So we ran a command like this while you guys were in class and captured a trace of what you're doing. Then we ran a little Perl script that went through this trace and sucked out. We wrote a little Perl script that went through this trace of packets and sucked out all the web pages that you guys had been looking at. And we made pictures of some of the web pages. So a lot of it, as I said, is pretty boring. So there's somebody who was looking to buy a micro drive. So they searched for Micro Center Cruiser USB high speed on Google. So we saw this page coming back from Google, which was the search request. And in fact, you sort of poke around some more and you see this person actually found the Micro Center website and went to Micro Center and apparently was trying to purchase this thing. So there were a couple people who were looking for movies, so people who were looking to see, looking for a movie to see. In fact, we actually saw this on both days, so it wasn't just one day that somebody was looking for movies, but somebody keeps coming to class and looking for movies. So the next one, though, is much more interesting. So we saw there's a couple of web pages that somebody is looking at a tool called GAIM encryption. And so GAIM encryption, GAIM is the open source AOL Instant Messenger client, okay? So, and GAIM encryption is a version of the open source GAIM client that encrypts data that gets transmitted over the network. And the way it works is that it when you install this tool, it generates you a public-private key pair, and then when you have a chat session with somebody else who's using this, also using this GAIM encryption tool, it sends that person your public key, and then it uses uses public-private key encryption and signing in order to protect information that gets transmitted over the network. So there was somebody who during class was looking at this tool, so we see they go to the project page on SourceForge where this tool is hosted, and they're clicking around, looking at what the tool does, and reading about it, and then you see that they download this tool. And in fact, after that, at some point, there's a whole lot of AOL Instant Messenger traffic that is going out over the network. So I'm just surmising that this traffic actually belongs to this person who downloaded this tool. And you can see that, in fact, the tool appears to be working, so that this traffic is not intelligible. And in other cases, when you see this tool actually goes across the network in plain text, the GAIM normally runs in plain text, and you can just see the entire transcript of the chat happening if you run this tool. So the kind of nice, the interesting, so there's a very interesting security lesson here, which is that sometime later in this particular trace of a chat, we see this same person. So this person one, their name is transmitted in plain text. So you see this same person even when using the GAIM tool, but you don't see their messages in plain text. But you see this same person now actually is talking, having a conversation, and they think they sort of say, oh, I downloaded this GAIM tool, now I can talk encrypted to other people. And yet there's this conversation where it's not encrypted. And they're talking, this sort of dialogue goes on, they're talking about somebody who's in class, and they say, why doesn't this person go to class anymore? And they're having this little chat session back and forth about why this person isn't in class. And so this is this sort of very, and the dialogue goes on, talking about how, talking about their design project and how they're worried about it. And it's sort of a nice example of a security problem, which is, or a potential security problem, right? Which is that this person actually did something that's sort of nice. They came to security class, they're learning about security in class, they go download this tool, and they think, okay, I've got this tool installed, now my conversations are protected. And then, as soon as they try and talk to somebody who isn't also running this version of the tool, their conversations are no longer protected anymore. So this is sort of a nice example of why security is actually a really hard thing to get right, because this person may have even believed that this person they were talking to had this tool installed as well, but you sort of don't know that it's not working until somebody points out that it's not working. Somebody violates goes in and is able to access this unprotected data. So this is a nice example of why security is hard and why sort of providing protection is essentially a negative goal, right? You never really know that you're protected until somebody points out that you're not protected. Okay, so that's just sort of a little lesson about security, and I hope that it sort of pointed out a reason in which, why it is that security is something that's both difficult and something that you might want to be conscious of. When you're sitting there, oftentimes when you're sitting there using your laptop, you have this perception that is, my information I'm sending, nobody's going to be able to overhear this information. It's going so fast and being transmitted so instantly that, of course I'm private. You feel very sort of isolated when you're having this communication until somebody points out that it's actually very easy. I mean, this is a tool that's standard on all Linux distributions, and it's one line that we type into our computer to get this information. It's actually very easy to do this. And so it's something that when you're transmitting sensitive information out over the network, over an email or in an instant messenger, you might want to actually think about whether or not you want to be sending this information out in the way that you're sending it out. Okay? So what I want to do now is come back to a little something we were talking about last time. Finish up our discussion a little bit of authorization, and then talk about sort of how we can start thinking about designing protocols that are actually how we can reason about the security protocols that we are using, particularly how we can reason about authentication protocols within networks. So if you remember last time, we talked about this idea of building up a secure communication channel. Then we talked about doing authorization on top of that channel, okay? Remember, authorization is this process of determining whether a given user should have access to a particular resource that they want access to. We talked about two main techniques for doing this, ACLs and tickets. So an ACL is an access control list. An access control list is just a list of users who are authorized to access a particular resource. And so the way typically an access control list works is that the system first authenticates the user to determine what their identity is, and then it checks to see whether that identity is authorized. That identity is actually on this access control list, and the user is authorized to access this particular resource they want access to. A ticket has a slightly different flavor, which is that typically a ticket, if a user presents a ticket, you don't need to actually check and see what their identity is. Simply having the ticket is sufficient to allow somebody to have access to a resource. The analogy here is very similar to a physical ticket in the real world. You go to a concert, you hand them a ticket, they let you into the concert without checking your ID. Tickets have so tickets, a common example of a ticket in the real world is, say, is in the web. On the web, you get these cookies, which are like tickets, and the reason that you want to use cookies instead of checking an access control list every time is that when you have a particular cookie, the system doesn't have to re-authenticate you in order to allow you to have access to the system every time you, say, revisit a page. So I have a cookie for, Amazon.com on my computer when I'm visiting the, when I'm in the process of purchasing some item from Amazon.com that identifies my identity and my shopping cart, and I don't have to sort of re-log in every time I request a new page from a new secure page from Amazon. Okay, so this model, the example we specifically were talking about was the web, and we had this notion of we had a browser and a web server, okay, and the browser and the web server we're talking over one of these secure communication channels. We said this channel is both authenticated, has been authenticated and is confidential. Okay, and authorization we said is authorization happens. There's some guard process that's in charge of authorization. This is our guard, and it sits in front of the services on the system. Okay, so when a request comes in to access a service, the web server passes that request on to the guard module, which does the authorization, and then if the request is authorized, it goes ahead and passes it on to the service. Okay? So what we've talked about, so what this is this sort of, we talked about, remember this, we have this notion of how we establish a secure communication channel. Typically we do that by exchanging, the one way that we talked about doing this is where B, for example, would discover W's public key somehow and then use that public key in order to exchange with W a shared secret key that they could use to encrypt all their communication. So I'll show that protocol again in a minute, but the question that we're really going to get at today is how it is that we want to focus in more on this question of how it is that B actually discovers W's, say, public key in a public key system, and how it is that B can sort of convince itself that, in fact it's actually talking with a service that it's actually talking with this service W. So if B wants to have a conversation with Amazon.com, how does it actually convince itself that this public key that it has in fact belongs to Amazon.com and that it's actually having a conversation with Amazon.com instead of with somebody else who's pretending to be Amazon.com or who has lied about Amazon.com's public key so that it can overhear Amazon.com's traffic. So we're going to focus in more on that now. So let's look at this. A simplified version of an authentication protocol. So this is going to be like that Denning-Sacco protocol that I showed with the broken example, or like SSL, for example, on the internet also sort of works in roughly this way. So we've got our browser, got our web server, and say we have some certificate authority. So this is the kind of picture we drew before. We said the browser sends to the certificate authority a request for say the public key of W. The certificate authority sends a message back which has, say, the certificates for B and the certificate for W, and these are just simply signed things that the certificate authority has signed that include the public key for B and W in them, so that's all certificates are. And then B sends a message to W, and there's some trickiness in getting this message right, but this message basically is a signed and encrypted message that tells W that it would like to initiate a conversation with it, and perhaps it proposes a shared key that it can use in that conversation, right? So it's a little bit tricky to actually make sure we get the format of that message right, and there's this bug with the Denning-Sacco protocol, but you get the idea. So W then sends a message back saying, perhaps asking the user to go ahead and trying to authorize the user, saying, okay, I agree that that's the key. Now, what's your name and what's your password, for example. And then once it's exchanged that name and password, then B is allowed to log into the system and access whatever B's resources B should have access to on the server. So the question that I want to focus on is this question about how B actually decides that the certificate authority is a certificate authority that it should trust. How does B initially establish the sort of authenticity of the certificate authority? So when we talked about authentication before, we presented this model that was sort of, well, you know, you're going to learn, you're going to decide that you trust somebody by, for example, having a conversation with them, right? You're going to, you know, I'm going to talk to you, I'm going to run into you in the hall, and you're going to say my public key is X, and then I'm going to be able to have a conversation with you. But clearly that's not what happens in the case of the internet, right? Like, for example, I don't go on the internet, I don't have to call up Amazon.com or call up my certificate authority and get the certificate authority's public key from them, right? Somehow I've already gotten this thing. And so we sort of want to think about how it is that we can actually exchange these keys and how it is that we can think about these, how it is that these systems can actually decide that they trust each other and that they are willing to authenticate each other. So to do that, what we're going to do is look at something called authentication logic. This is also the specific version of authentication logic we're going to talk about is something called BAN, B-A-N logic. B, A, and N just stand for the names of the three people who proposed this thing. So it's not a specific acronym you need to know. And so what authentication logic is going to do is it's going to allow us to reason about these protocols for exchanging, for deciding whether or not we should authorize somebody to, we actually trust something like a given certificate authority. Okay, so let me just give you, to think about this a little bit more, let's look at a specific example. So suppose that you receive a message over the internet. Okay, suppose this message says, well, it's some message M, and the message says is signed M with some key K, call it K sub A. Okay? And suppose that the contents of message M are M equals give A your credit card number. Okay? So this might be a valid request, right? We might be purchasing something from Amazon.com, right? So that in that case, you might think that it might be okay for we might expect to receive a request like this, right? But the question is, so this thing was signed with KA, and the message said give A your credit card number. But how do we actually know, and you know, maybe A in this case is give it to Amazon.com, and we know that we're talking to Amazon.com. And so if this in fact were an authentic message, we would be, you know, we might not be that, we might be actually willing to give Amazon our credit card number. But, so how do we actually know though that this message that KA is is the key that belongs to Amazon.com, right? So we want to answer the question, how do we know that, or trust that KA, we're going to say, speaks for A, okay? So this notation speaks for just means that KA, if we see something that for example, is signed with KA, that claims to be from A, we might actually trust, in fact, that this thing came from A. Okay, and we want to know, we want to sort of determine. We're going to try and answer the question of how do we trust this? Okay, so one way that we might trust that this is true is if we had heard, for example, that B, we had heard some message, let's call it M2. From somebody B that had said that this message said KA is A's key. Okay, so one way that we might start thinking about, one way that we might trust A is if we'd heard from somebody else or heard from some other place that KA was A's key. Okay? But now we're sort of, this is kind of a slippery slope, right? Because now you say the question, well, how did you determine that you trust B's key, right? So there's sort of this infinite process that you could end up going through. That doesn't sound like a very good idea, okay? So one way in which this sort of, we might bottom out this recursion, we might end this sort of infinite process of collecting keys, is if we actually, sort of in the example I gave you, we'd heard from one person at some point, you know, suppose there's a B and a C and a D and an E and an F, and then eventually we get to F, and F is our friend who we had talked to, and F had said, my public key is this, and here's the public keys for a few people that I know, right? So you might trust F, and you might believe that F knows a few other people, and then those people who F knows might in turn know a few other people, and eventually we might be able to sort of have this web of interconnected people all of whom we trust. Okay, so one thing we might end up with, so this would be sort of a web of trust. Okay, so we might be able to build up a web of trust like this, but you could imagine that these relationships are pretty complicated, right? That, you know, each person, for example, B might trust a few people, and C might trust a few people, and D might trust a few people. And every time we're presented with some message, we need to have some sort of principled way of thinking about whether we have a set of these signatures, or a set of these keys, for example, that actually allow us to decide whether we should accept this message or believe this message or not. Right? So if we had a web of trust like this, we would sort of need some way of going about validating or verifying that, in fact, these messages were messages we should trust. So that's what authentication logic is really all about. So this is the simplified ban logic that's presented in the text. It's on page 1185. If you want to copy it down, I'll try and leave time for you, but in case you want to just copy it out of the text, you might not need to worry about copying down the exact logic here. So there are 3 rules in this simplified authentication logic, and they correspond to this. They use this notation, this speaks for notation, and they're also going to use some notation that we call it that says this says notation. Okay? So what this rule says, so this says if A says B speaks for A, then B speaks for A. Okay? So this sounds like sort of an obvious statement, right? What this depends on, so what it's saying that A says something means that if we hear A say something, that means that we actually sort of, A told us, and we believe that this in fact was A who told us this thing, right? So in order for A to say something, we have to actually believe that it was, this can't be a message, for example, that we received over an untrusted network, right? This has to be, you know, I sat next to A in the hall, and A actually said, B speaks for me, right? So in this case, B might be, for example, some key. Right? So A might say, my public key is KA, okay? If that is true, and in fact we believe that A is the person who said this to us, then we might be able to infer from that this key KA actually speaks for A. Okay? So this is what the first rule is, and this just gives us a way of sort of, this is the base case of you have something that you sort of have a trusted communication channel with communicating with A, and you can use that trusted communication channel to actually build up some belief about, say, for example, a key representing somebody. Okay? So now the next rule is one that sort of says, given that we have some belief about somebody, you know, one of these things, like, for example, if we know that B speaks for A, we know what A's public key is, and we overhear B saying that A says X, then we might believe, in fact, that A says X. So a simple example of this is, suppose we get a message that's been signed by this key KA. Okay, so we said, and that this, so if we see that, then we might in fact have a rule that says we might believe that KA actually says this thing. The KA says that A says M. And we might believe that KA says this because we believe that this sign, this sort of sign primitive actually means that if we see something that was signed with KA's key, that in fact that thing was generated by KA, right? That nobody else could have generated a signed message that worked with KA. Okay, so we can use this now to, for example, build up we can receive a message from A that's been signed using KA, and we can in fact believe that, you know, A said something, okay? And now the final rule that we have is sort of a transitivity rule, which is a way of sort of which is a way of sort of expanding this web of who's related to whom. So this says if B speaks for A, okay, and A speaks for C, then what we're going to believe is that B speaks for C. Okay, so this is just a transitive relationship. So for example, if we know that KA speaks for A, and we definitely overhear B saying A speaks for B, right? If B delegates, if says A, everything, you know, that A can speak for me, then we might believe that key KA also speaks for B. Okay, so this is a simple transitivity relationship. So the idea with these rules is that we're going to be able to use them to actually think about whether or not so we can sort of, anytime we have this thing isn't quite far enough down. There's a then here that should say then B speaks for C. Sorry, that got cut off. So if we have a set of rules like this, then we're going to be able to apply these rules sort of anytime we have a conversation to decide, again, whether we actually trust the people who we're communicating with. And you may have noticed when I was talking about this that I had there was sort of a lot of statements like, if we believe that sign of X, you know, that sign X, nobody can actually fake this protocol sign X, right? We believe that that signing a message with KA is as good as actually, that nobody could forge this message that was signed with KA, for example, right? If we believe that that's true, then we can say KA says this thing. So this authentication logic is full of a lot of these sort of like, if we believe this thing is true, kinds of assumptions that we're going to be making. Okay, is there a question?
The third rule, but what part?
Sorry,
I can see the bottom part on the left.
Okay.
I just mean, I don't know, like, in the example, which part is C?
Oh, okay, so in this case, sorry, you're right, my example is kind of confusing. In this example, B is actually C. So, sorry, no, it's
KA speaks for A.
Right, so KA is B, A, right, so it's sort of, so it says if B says that, if we know that B speaks for C, if we know that A speaks for B, right, then we might be willing to believe that KA actually speaks for B, given that KA speaks for A, right? So we have this transitivity kind of a relationship. Sorry that that notation is a little bit confusing, I agree. So, okay, so the challenge here is that we want to try and make, so we're going to be making, anytime we're using this authentication logic, in order to actually determine that somebody definitely said something, we're going to have to make some sort of set of assumptions about what we trust and what we believe. So, and one of the things that's important anytime you're using this authentication logic is to actually make these assumptions as explicit as you can, okay? So let's look at a set of assumptions that we're making here. So I said something like, when I see a message that says sign M, comma, KA, right? And then I infer from that A says M, right? Assuming that I already know that and I know already that KA speaks for A. Okay, so if I have something like this and I make this inference that A says M, given that A says M, given that KA speaks for A, and then I saw this sign thing, right? I'm making a set of assumptions when I do this, and I'm making a set of assumptions in particular about what this sign protocol does. So I'm assuming, for example, that the sign protocol is actually that sign is actually secure in some way, right? So I'm assuming that this signature is not forgeable, right? That somebody else couldn't have generated a signature unless they actually had access, for example, to the private key or to the private key of A, right? So they wouldn't. This signature is not forgeable. I'm also assuming, for example, that if this is a that I'm also assuming that any private keys are actually private, right? So I'm assuming that, for example, A hasn't gone out and broadcast its private key out to everybody else in the world, right? Because if A had done that, then I wouldn't actually know that this message that A actually said M. It could have been anybody who said M, right? So I would be in trouble if that were the case. So anytime that I sort of make this inference from seeing a sign like this, then that suggests that I'm sort of making these two assumptions. And, you know, it's not that these assumptions are wrong or bad, it's just that it's good to think about explicitly what they are, right? So assuming that the signature is not forgeable, well, we all know that cryptography can sometimes be broken, right? It's not that cryptography is totally foolproof, but we may have a relatively high confidence that this cryptography is going to be difficult for somebody to break, right? And, well, assuming that private keys are actually private, you know, we might be willing to assume that we might sort of know A personally and believe that, well, you know, A is an upright, upstanding individual. You know, we're going to trust that she hasn't gone and disseminated her key around everywhere in the world, because that wouldn't really be in her interest, and we take her to be a trustworthy person. So this is a bit of a leap of faith that we're making about this, right? But if we believe those two things, then we can in fact infer that A says M when we see a message that's signed with KA. Okay? All right, so let's look at this, and let's look at a little bit more, another example that works with this sort of public key cryptography that we talked about, say in this example of this authentication protocol here. Okay, so suppose suppose that A tells me my public key is KA pub, and this is done over a secure communication channel like in-person communication. I might then infer that KA pub actually speaks for A. Okay? Now suppose I see a message that's been signed with KA private. This message, so I might say that then KA private says, so this is an inference, I might say KA private says that A says M. Okay? The question now is, and what we want to ask now is, okay, so should we, given this, should we actually believe that A said M? So I saw a message, I know what A's public key is, and I trust A's public key maybe, and I saw this sign thing, and now I need to think about, you know, okay, do I believe now that A actually said M, given that I saw a message that was signed with KA private, Okay, well, so there's something obviously that we need to do, which is that we need to verify this message. So suppose we go and we run this verify step on this message, and that this verify comes out to be true, right? So what verifies, so I verify using KA pub that in fact this message was appropriately signed. The verify says, yes, this message, the signature on this message checks. So now should I believe that this message actually came from it, that A actually said M? So that depends. Right? There's a couple of conditions which we might, again, there's this sort of set of assumptions that we're making. So one thing we're clearly doing is assuming that this crypto system is secure. We're also believing that this verification step actually this verification step actually gives us that by taking something that has been signed with the private key and then verifying it with the public key, that is as good as A actually saying something. So one thing clearly that depends on as well is that the crypto system is secure. Sorry, I'm just going to erase some text here because the bottom got cut off, so you guys can read. Okay, so there are a couple of other assumptions though that we're making. So one thing is that it definitely, again, requires that KA private has actually been kept secret. And furthermore, it requires that A didn't lie to us about what KA public was, right? Because if A had given us a wrong KA public, then somebody else could have signed this message, and then we might try and verify the message using the lied about KA public, and then we might be in trouble. Okay, so again, this is similar to this example with just a single, just KA, but just showing how it works with public and private key encryption. Okay, so it's this case that, again, we sort of need to always think about making our assumptions as explicit as possible. Okay, and that's really what it's about. Deciding that we trust, for example, that a signature is true is analogous to deciding that we have to sort of trust that we trust the cryptography. It's possible to apply this authentication logic in other environments as well that aren't necessarily based on cryptography, right? So I might, for example, instead of trusting that the cryptographic system works, I might trust that a particular communication channel is secure. right? So for example, if I pick up the telephone and call you and I say, you know, give you some message, you might trust that it's me because, say for example, you believe that it wouldn't be possible for somebody to fake my voice and you recognize my voice because you've come to lecture so many times, right? So that would be an example of a way in which you might sort of decide that you trust that something is actually true, and that would be an assumption that you're making about somebody not being able to validate my voice. So the point of authentication, fake my voice. So the point of authentication logic is that it gives us a way to kind of reason about these, it gives us a way to reason about these kinds of deductions about whether or not we actually believe that somebody said something was true or not. Okay, so that's fine. We still, though, at least when we're using public and private key cryptography, we still haven't exactly answered the question of how we go about establishing this initial trust step, right? So we said we might establish initial trust by, so there's always sort of at the bottom of this is we have to actually physically overhear somebody say something over a secure communication channel, we think, right? We have to have some way of getting this first step that says, you know, getting this first rule where A says M in order, A says that my, for example, public key is something, so we can learn A's public key so that then we can bootstrap communication with A. We haven't yet answered the question of how we actually exchange these keys, except for by this one method that we talked about, this web of trust method, okay? So there's this question about establishing some initial trust, okay? So one way we might do this is using this web of trust approach, where I get a little bit of I meet a friend, that friend gives me some information, tells me about some other people, some people who he or she trusts, and then those friends' friends in turn know a few people, and eventually we establish communication with everybody. So there are some computer systems that work this way. In particular, there's a system called PGP for Pretty Good Privacy, which is an email-based privacy and encryption system that works this way. And there are, in fact, websites that are dedicated, that you sort of, the idea is you find somebody else who has used this system, you share, you exchange public keys with them, and then once you have a few public keys, you can sort of build out this web of trust to everybody else by trusting people who your friends trust, okay? The problem is that, one, clearly the internet doesn't work this way, right? So you don't have this kind of a system that you're using on the internet. And two, these kinds of systems are very difficult to set up and maintain, and there ends up being some centralized administration that's sort of, you end up with having to have some sort of way, it becomes very difficult to actually disseminate these kinds of public keys in these kinds of systems. So the way this works is there's a centralized website, there's a website for PGP that's a giant database of keys, and you sort of try and discover people's keys by walking this web of trust, but it tends to be difficult to use. Okay, so let's talk a little bit about how this actually works in the context of the internet. So suppose that this browser here, there's actually some person P who's sitting in front of this browser. And there's some questions that we might want to ask when we're thinking about deciding whether or not we trust this person P, okay? So one question that the web server might ask is, does W know or trust person P, okay? Or how does it? Okay, so if this is a commercial website like Amazon.com, actually the trust story turns out to not be that complicated, right? Amazon.com doesn't really care that you're who you claim to be as long as you give them the money that they want, right? So you can go on and tell them that you're Oscar the Grouch. They don't care as long as you give them the money that they want for whatever it is that you order, right? That's all that matters to them. So in fact, what Amazon does is they don't actually know who you are exactly, but they might decide that they trust you because the credit card company, the credit card number is good, and is verified by the, say, credit card company. So when they try and charge your credit card, they get the money, they're happy. There's this other question, though, which is that about how does P trust W, okay? And the way that this works on the internet is basically the same, it's basically like the way that this authentication protocol that I've shown you here works. This is how SSL works. And it turns out that it's the sort of, whether or not you should, it turns out to be very subtle or very sort of, it can be quite hard to actually convince yourself that you should trust a given website if you actually start drilling down on it. So there are some issues. So the way that it's going to decide that it trusts W is by checking with some certificate authority. That's how it works on the internet. And there's some issues with this, okay? Which is, how does the certificate authority authenticate W? Okay? How does the certificate authority decide what W's key was, and how did they securely exchange keys with W? How did the user get the CA's public key? And then what happens, say, what if somebody's private keys are stolen? For example, W or the certificate authority's private keys are stolen. So what I want to do is just sort of show you at a high level how this actually works on the internet. I thought it might be instructive just to see an example of what is actually going on the internet, and to kind of illustrate how some of these issues are and are not properly addressed by the current sort of SSL-based internet architecture. So I have a couple of websites open here. I have an Amazon.com website, and I have in this case, it's an Apple developer website, both of which you'll notice have HTTPS URLs associated with them. So in this browser, if I click on this little secure icon here, almost any browser would have a similar sort of a feature, a little lock somewhere that's when you're viewing an HTTPS page. What I see is something that it lists all the certificates that are associated with this, it lists how it was that this site actually decided that this was a secure site that it should communicate with. So when that little lock appears, it means that my browser has actually decided that it trusts this site, okay? We're at the point we've already said we trust this site. And the reason that we trust this site, it says, is because, well, we have this site is www.amazon.com, and we have a signature we have this certificate for this site that was issued by RSA Data Security Incorporated, okay? So you might say, who is RSA Data Security Incorporated? I've never heard of these people. I've never exchanged any information with them. I've never, but they're the certificate authority, okay? So that's the person who signed this thing. I can look at this, I can sort of drill down on this, and what you'll see is, well, some information about Amazon.com. So this is the actual certificate itself. This is some information about the certificate authority, including information about what algorithm the certificate authority has used to generate this certificate. And then now what we have is this public key information is the actual public key that corresponds to Amazon.com. Okay, so this certificate contains Amazon.com's public key that was encrypted using the RSA algorithm. And then there also is some information, this signature that goes with this public key. So this is the signature that was signed by this RSA corporation. Okay. If I go to a different site, like for example this Apple site over here, we see that this thing was actually signed by somebody else. Okay, so this certificate is signed by somebody called VeriSign Incorporated. And again, you have no idea who VeriSign Incorporated is, but you'll notice that these are two different secure certificate authorities. So it's not the case that there's one master certificate authority out there on the internet that's in charge of everything. Okay? So on a Mac anyway, and the same is true of most other operating systems, there's some way to go and look at, there's a way that we can go and look at the actual list of all the people who we trust are. So this is sort of an instructive thing to do, to go and see who it is that you actually trust that's on this computer. So what this list is, I can click on this, I don't know if you can see that, yeah. This certificates over here, this is a list of all the certificates that on this machine that are I have and where I would accept things from, okay? So you can see that there is a very large number of certificates that this machine has installed. These are not just certificates, but actual certificate authorities, people who I would actually trust to sign a website from a certificate, to sign a communication with a given site, to provide me with a certificate for, say, some web server that I want to communicate with. Okay? And so what's going on here is, so for example, one of the things, and these things now the question is, okay, so where did these things come from? They came from one of two places. Either I added them to the system myself. So in this case, I have, for example, an MIT certification authority, right? So if any of you have ever used MIT certificates, like when you're logging onto WebSys, in order to be able to access that system, you had to add support for a given certificate to your browser, okay? So this MIT certification authority is a certificate that came from MIT, and this web browser, and this keychain thing, which shows me all my certificates, has this funny sort of message that says this certificate is not in the trusted root database. The reason it says that is because I just got this certificate off the web. So this is a certificate for the MIT Certification Authority. I just got this certificate for the Certification Authority off the web somewhere, right? And I didn't do something that it wanted me to do to actually verify that this, in fact, was a legitimate certificate from this certificate authority, right? So somebody could have put this thing on the web and said, this is a certificate for the MIT Certificate Authority, and you should use it to discover certificates for anybody who claims to be coming from MIT.edu. They could have lied about it, and then I would be in trouble. So it's possible that this is a fake certificate for the MIT Certificate Authority. But I sort of have made this assumption that it's not, because I downloaded it from a website and I believe that in fact this is a valid certificate. The other things you see here, see this large number of certificates. For example, one of the ones that we see is the, let's see if I can find RSA here. This RSA security, right? So here I see RSA security, and this thing, it actually says this certificate is valid. So now there's this question about, okay, where did RSA security come from? And the way that this works is that this browser and in this case, the operating system itself has actually been shipped with a bunch of certificates from a bunch of different certificate authorities, okay? And so these have been installed by the operating system manufacturer, and I'm saying, okay, I trust Apple to have gotten the appropriate certificates and loaded them appropriately into the computer. And anytime you download a browser, basically that browser already has these certificates, sort of has a set of certificates for a set of certificate authorities already installed in it. And that's where all of these base certificate authorities come from. So you can see that when you're using one of these things, you've already placed quite a bit of trust. You've made a number of assumptions about sort of who you trust and what you should trust just by using this system. Okay, so we've answered this question now about, okay, where did the user get the public key for their certificate authority? Well, either they explicitly added it by downloading it from a website, say, for example, or it came with their browser. So what about this question, how does the certificate authority authenticate an actual website? So how does Amazon.com get a certificate from, say, VeriSign? So the answer to this turns out to be that, well, Amazon.com probably paid VeriSign some money. And it's not clear what else, it's not even clear you can say that, but in the case of VeriSign, you're probably pretty sure that Amazon.com paid them some money. And VeriSign, you could probably go to the VeriSign website and see a list of things that they claim to have done in sort of authenticating Amazon.com, right? So they may have forced Amazon.com to present them with some information that actually suggests that they're the company Amazon.com, or they own some right to the name Amazon.com, or that they're incorporated under the name Amazon.com. So basically, the certificate authority has some protocol that it uses to authenticate W, and that protocol, we don't know what that protocol is, but you're sort of implicitly trusting that all these certificate authorities that Apple has already approved for you, in fact, use some process that will be reasonably assured of guaranteeing your privacy, or guaranteeing that the websites that you're connecting to are in fact valid websites that you should feel comfortable giving your credit card number to. Okay, so you can see that this is a little bit dicey, right? It feels a little bit like it's not clear that this is incredibly secure. And then the last question is, well, what if your private keys are stolen? If your private keys are stolen, in this particular example, the certificates that you have from, say, Amazon.com, or from one of the, so if Amazon.com's private keys are stolen, or one of the certificate authorities' private keys are stolen, then you're in trouble. These certificates typically have expiration dates associated with them, but these expiration dates are often years or more into, like a year or more into the future, right? And so you're going to continue to trust that certificate until the certificate expires in the future, when you'll go try and get a new one. For that whole time that you trust that certificate, somebody who had access to the private keys from that certificate authority or from that website would be able to pretend to be that certificate authority or that website. So that might be problematic. Okay. So that's sort of the end of this little discussion about how certificate authorities work. I hope you can see that this authentication logic is sort of a way that we can start to get at thinking about what the trust assumptions that we're making are when we're using these systems. So this wraps up our discussion of security, and what we're going to do, and we have one class session left, and the last class session is actually going to be a guest lecture, and it's going to be somebody talking about sort of how law and computers and technology interact with each other. So we're going to kind of step back and talk much more about high-level pictures like policy and law next time, and hopefully it'll give you a good picture of sort of a good wrap-up for the whole class of 603. So we'll see you next time. Please come to class because there will be questions on the guest lecture on the exam, so you want to make sure you don't miss it. Okay?